next year. So hopefully we will have the time to do the quiz on the superposition. It's a different version of it, trying to reinforce it. So we'll talk about ADC this time, since you did a little bit about ADC in the lab, but it's the ideal ADC. You still have no concept about what how the ADC operates or how to design ADC. So it's analog to digital converter, and if there's an analog signal, continuous signal, but we are only sampling 4 points because of the sampling rate and resolution of the ADC. So this is the analog signal, okay? But because of the finite sampling rate, we are not able to sample every single point. That makes sense, right? We just won't be able to sample every single point on the continuous analog signal. So for example, we are able to sample these points. And the ADC is able to convert them. If it's a 3-bit ADC, it's going to convert them into its digital form. If this point, for example, is 100, this is 10110, for example, okay? This is 101, this is 011. In terms of volts. And eventually, you are getting, for example, this point in this period, conversion period, you're getting 1, right? 100 means it's going to be like 100 to represent 1 point. These are also voltages, but they are digital signals, digital voltages, but still voltage, just the potential difference. Okay, but they are only 1 zeros or 5 volts and 0 volts, depends on the voltage, the logic of the power supply of the circuit, right? So it's going to convert that point into 100 and ignore all the other points on the curve because of the finite sampling rate. For this one, for example, it becomes 1, 1, and 0. Okay, for this period. Okay, and for this one, it is 1, 0, and 1. And for this one, it's 0, 1, and 1. Okay. And if you plot it, it becomes, this is what? This is 4, right? Becomes 4 until here, the end of the conversion period, and jump to 6, and come back to 5, and then come back to 3. So if you digitize this signal, it becomes this in the computer instead of this. That's what you saw in the lab, and that's why you're getting stars.
How is it assigning the values of the 1, 0, 0, 1, 1, 0?
How do you mean by assigning?
Like, how is it getting those? I get that they're numbers, but
yeah.
What if it's in between 2 values that like in between the resolution?
It samples, this is a really good question, it samples it and hold it. There's a certain circuit called sample and hold.
So it holds it until it goes up to the next value.
Yeah, holds until the next cycle. So there are clocks controlling the cycles. So it sample it and hold it. So what happens is it samples this voltage and hold it in the capacitor and hold it for the conversion period. So the ADC is going to be super busy with the conversions and to form all the digits. How does it form it? We're going to talk about the successive approximation register ADC, which is one of the maybe 5 different architectures of the ADCs. It's called SAR ADC, and it has a SAR architecture or algorithm running behind the scene to do the conversions. So sample it, hold it like this, right? So there's your sample and hold circuit, sample and hold it, then the voltage will stay there. So ADC will be just very busy doing that conversions. And it's called successive approximation registers ADC. I'm going to talk about how that works in a bit. So that's a big picture of the ADC, and and there's a theorem called Nyquist-Shannon sampling theorem. You learned that in DSP as well. So it defines the sampling rate. The sampling rate has to be equal to or larger than 2 times of the maximum frequency of the signal. If the sine wave, if the signal is a sine wave, then it's just a monofrequency signal. There aren't any components of the signal. It's okay if you are not getting that, if you haven't taken any of the signal classes. But this is only one frequency in this sine wave. Okay, so this frequency, for example, is 1 kHz, and this one will be the F max because it doesn't have any smaller frequencies. This is just F max. So the sampling rate, if you are sampling this sine wave, this analog voltage, the sampling rate, which is what I just showed you here, you sample it, right, and hold it, and sample and hold it. So the time period between these two, and you convert it. For example, this is T, and so 1 over T will be the sampling rate, the sampling frequency. Okay. So the sampling frequency has to be equal to or larger than 2 times of the frequency of the signal. If you have multiple components in the signal, it has to be larger than the 2 times of the maximum frequency of the components in the signal. And why that makes sense? For example, you have this sine wave. Okay, I mean this is the bottom line, this theorem, but actually you'll never sample at that rate. It's gonna have a hard time to recover it. So it's better to sample at a faster rate so you can recover a better form of the signal. However, if you sample the signal at a higher rate, then it takes more power and also slows down the conversion. So it's a trade-off there. But the bottom line, according to the Nyquist-Shannon sampling theorem, which is Fs has to be equal to or larger than this. So for example, this is 1 period of the signal, right? And if you sample only once, which is 1 period you sample once, which means Fs equals Fmx. Doesn't meet this requirement. Can you recover a sine wave by just having 1 point? You can have anything on that point. Okay. However, if you sample 2, if you try to recover it, at least you are getting like this, right? Hopefully, I don't know, but still hard. At you know that there's a peak, there's a reverse or the negative peak over here, but it's still not ideal. Okay, so when you are designing ADC, you have to keep in mind that the sampling rate has to be a lot larger than 2 times of the Fmax, but we never use actually Fs equals to Fmax. Right. I think there's an example about aliasing. If you have a slower sampling rate, you are getting something like this. Okay, so the faster sound wave is the original signal, but it's sampled at a slower rate, like 1 point here, 1 point here, 1 point here, 1 point here. But when you recover it, it looks like this instead of the original signal. Okay. So let's talk about the ADC's DNL and INLs. It's very similar to the DNL and INLs of the DACs we learned, and you have to know how to calculate it in order to get a good score on the quiz or exam in the future. different from the DAC's DNL curve. First, we want to look at the quantization errors. It's a new concept over here, but it's very simple. So the x-axis is what? It's the ADC. ADC is transfer curve. Okay, so ADC's transfer curve, we have x-axis at the input. So the x-axis will be what kind of input? It's ADC, right? So the input has to be analog input. So the output is a digital output. What's the resolution of the ADC? What's the resolution of the ADC? This should be a 1 second answer. Remember when we talk about the resolution of the DACs last week, so the answer should be how many what? Bits, right? So how many bits are here in the ADC? No, apparently it's 3. That's the output of the ADC is a 3-bit, and 2 to the third power will be 8. So it's a 3-bit ADC. Pretty poor resolution. That's why you are seeing huge stars. But you can smooth them out using a low-pass filter later on, but still not ideal because it's not able to resolve smaller changes. So the x-axis will be the analog input, and the y-axis will be the 3-bit digital output. And the quantization error here plots the difference between the converted value and the ideal value. So you are expecting, no, not expecting, but the ideal curve is a dashed curve, the line, linear line in the middle. That's the ideal curve, right? But however, it has a poor resolution. So you are not getting all the points on the ideal curve. Instead, you are getting zeros until 1/8. So there are errors in between these 2 points. And if you directly plot it, it's actually using the ideal values minus 0. Right? So it started with 0 and start increasing to 1 LSB, and then drop to the next to 0 because it reaches that value. See this point and the dashed curve overlaps, which means it's getting a 0 quantization error. That's a concept. Here's the name of it. Quantization error. It's just the errors at each time point. Does that make sense? Are you able to see the errors like this in this curve? Right? It's increasing from 0 and then to 1, and then drop to 0. Make sense here? So it's changing from 0 to 1, okay? And it's considered, so when we describe the quantization error, we say it's from 0 LSB to 1 LSB. And there's a better way to do it if you can modify the design of the ADC and shift the value to the right by 0.5 LSBs. We don't have to worry about how to design ADC to make this happen. Just think about that. If we are able to make this happen and move the transfer curve to the right-hand side by 0.5 LSB, and now the quantization error changes from 0 to 0.5 LSB, and then drop to negative 0.5 LSB. So this is considered as an improvement. So it becomes, the quantization error becomes plus minus half LSB instead of 0 to 1. So it's changing too much until to 1. But now it's just swinging around 0 with a smaller range. It's plus minus 0.5 LSB instead of 1. So when we are looking at the ANL, DNLs, we use the shifted curve in here instead of the first one. So now this is a shifted curve with the quantization errors plotted, but we usually don't look at it here. We just want to find out the DNL and INLs. So the first curve, we're going to try to find out the DNLs first. DNLs. So the way to find it is similar to the DACs, the differential nonlinearity, DNL. Similar to the DAC, we compare each step, the step size, the real step size to the ideal step size for 1 LSB. It's very simple to do it actually. If you look at the curve, I can tell that super quickly because it's super simple. I just look at the step size over here. So this is exactly what we expected. And this is also, so for the shifted curve, keep in mind that DNL1, where the first, the step 1 should be 0.5 LSB, so shifted, and you actually shifted to the left, not right. So for this one, for the last one, which is DNL7 or the step 7, it's 1.5 LSB, which is the ideal one instead of 1 LSB. Just keep in mind when you are subtracting that from the real one. But so this one looks normal, this one looks normal. And this is 1 LSB looks normal, and this doesn't look normal. Okay, so this larger one, when you look at it, actually recommend you guys rotate it and just look at from here, like the DACs. So this is DNL2, 010 is 2, right? So this is DNL2, which is 1.5 LSB. Have to minus the ideal step size, which is 1 LSB. So DNL2 becomes DNL2 is, keep in mind the concept here is, the definition here is actual step width minus the ideal step width. So the actual step width here is 1.5 LSB minus 1 LSB. And you want to know the footnote of the, what's that called? The DNL plus DNL, the number there is that a footnote? No, it's not a footnote. What's the name of this? What's the name of this number? Subscript. So the subscript for the DNL here is y-axis value, the label here, right? And this equals actual minus the ideal. And the ideal is always 1 LSB, so it's very easy to remember. So the actual is whatever you observed here. Pretty easy, right? Okay, so now we got DNL2, which is 0.5 LSB. Could tell me the next. DNL what? Yeah, it's negative 0.5 LSB, right? What's next? Is 0. DNL5. It's another negative 0.5 LSB. And DNL6 is positive 0.5 LSB. And DNL7 is this ideal size. So keep in mind the ideal curve, the original curve looked like this, right? So the last one is 1 LSB because the first curve start jumping up at 1/8. But now since we want to reduce the quantization errors, we shift to the left. So when we shift it to the left, this one is being stretched. It's kind of stretched from 1 LSB to 1.5 LSB. So the step 7 step 7, the ideal size is 1.5 LSB, and you are getting 1.5 LSB here. So DNL7 is 0. Okay, clear on DNLs. Now let's look at INLs, integral nonlinearity of the ADCs. It's a little confusing here because the textbook has the ideal curve moved up a little bit, but I think since every point is moving up, so it's not actually affecting the results. It's just easier for calculation. Anyway, so let's just use this moved this curve over here, because you can see the last one having the curve plotted from 0. Okay, and now this one could be confusing because Dr. Baker shifted the curve to the left a little bit. But because the integral, you are subtracting everything, so the ideal curve and the actual curve getting subtracted at the same time, so it's not affecting the results eventually. Anyway, so let's look at the INLs. The INLs are not subtracting the step size, it's subtracting the actual value here. It's still looking at the y-axis, and so you are looking at if the point is right on the dashed curve. If it's not, then there will be an INL. Okay, so so if you look at the conclusion here, INL 0, 1, 2, 4, 0, all these are zeros. Now let's take a look at them, each of them, see if they are zeros. 0 looks okay, it's 0. 1, it's on the curve. 2, the curve. 3 is not because it's off a little bit, all right? But 4, it is. See, it jumps to the curve. 5, it is. And 6 is not, and 7 is. So all these are zeros for the INLs, and you only got 2 of them are not zeros. One is INL3, which is over here, and when you are doing the subtraction, you still have to rotate it. So just subtract these numbers, this value from this. Subtract that from here. You know what I mean? So use this one to subtract this value when you are looking at this x-axis. So assume this axis is y, okay? And this point here is definitely higher than this one. And just do the subtraction, use the higher one minus the lower one and get the difference of the heights. So that's the INL. It's an easier way to calculate it. The textbook may shows a different way to do it, but that's how you get all the correct values. So now let's calculate this one. So this is INL what? 6, right? It's INL 6. So this point is not on the curve. If you compare the heights, so what's the INL here? No, this is lower, right? If you rotate it, the actual one is lower, and the ideal one is higher. So it's actually a negative number, so it's negative 0.5 LSB. So if you design the ADC in the future, these are the most important 2 specs of the ADC. You have to report it to whatever on the paper or to the reports, in the reports, for the INL DNLs of the ADCs or DACs.
Why is the equation value ideal? For that ideal
It's actual minus ideal. That's how it's. Yeah.
So
No, it's looking at the height. So this is actual. Here's lower. If you treat this one as a y-axis, right? So the actual value jump to here. And look at the y. Which one's higher? Yeah, the ideal is higher. right? So the actual minus ideal becomes a negative.
So that equation is supposed to be sideways, not straight like that.
Hmm.
But the ideal, if you do it like this, then according to the y-axis, the digital y-axis, the ideal is
It looks like the difference is here, I think. That's how it's being defined, right? The reason I rotate it is easier to look at, but it's actually comparing here, or you can treat it as the left hand side one will be this is actual, right? This is ideal, and subtract the lower value on the left, right? It's still negative 0.5 LSB. It's the same value here. Okay, so when you work on the homework assignment, since still Friday this week, I'm pretty sure you haven't started yet. Have you? No, you have? Okay. Oh, not this one. I'm sorry. This is the easier one from last week. It's still Friday. It's pretty easy. We already covered everything. And homework 2 is due next Wednesday, which you have to. It's a DAC, not ADC. This ADC can be confusing on the textbook, but let's do a DAC so it's similar to the ADCs, DNL, NLs. So this is one of the problems from the problem list in the end of the chapter, and determine the maximum DNLs. So you have to find out all the DNLs. Then you can find out the maximum.
So we don't do that.
You do it.
Oh, you do both.
What do you mean? What do you mean do both?
Homework 1 and
Homework 2 is due next Wednesday. Homework 1 is due this Friday.
Okay.
This is homework 2 is due next Wednesday. Okay. I just want to show you how to do it in the right way, so you are not making a lot of errors. So this one, okay, you got digital input, right? It looks different from the transfer curve we showed on the textbook. So you got a digital input, voltage output. So that's the DAC because the digital input, okay? And for DNLs, we are looking at the step size, right? The actual step size minus the ideal step size. So we have to know the step size in order to find the DNLs. So the first step to do this homework is you just have another column and just call it step size and find out the step size for each number. Just list all of them. And then have that's it for DNL. You have the ideal step size and just the subtraction, just minus 1 LSB. So you can find out every single DNL. Or in addition to that, or when you are calculating NLs, I think it's better that's the second problem, right? And it's better to draw the transfer curve so you can see all the NL, DNLs very clearly instead of imagining in your mind the picture in your mind. You can make a lot of mistakes by doing that. So it's better to just draw the curve. Can you draw the curve just from all the numbers given here? The transfer curve? Yeah, you can X and Y's. That's everything you need to know. X and Y's. Okay? Be patient. Can be pretty tedious, but be patient so you're not losing any points. It's a pretty simple homework assignment. Don't lose any points on it. Okay. So let's talk about the architecture of the SAR ADC, and we'll talk more about it on Friday. Let's start the topic today, and I'll give you 10 minutes to work on the homework, to work on the quiz. Okay. Successive approximation ADC. And Arduino's analog input, just right behind that pin, the A0 to A, how many analog input it has? Like 5, forgot. Doesn't matter. So it's all the A something pins on Arduino. Right behind it is a SAR ADC. So it's a 10-bit SAR ADC being used for Arduinos. Low cost, high resolution sometimes, but not the highest. Can be 8 to 18-bit. Low power consumption. That's the features of the SAR, okay? Can be used for wearable devices. Here's a schematic of it. The top level schematic of the SAR ADC. So V in, the analog input, comes in, analog input comes in, and being fed into the sample and hold circuit. Hold it at the DC value, so the ADC can work on it to convert it into a digital values. And sample and hold will fit into a comparator. Comparator is op-amp, and there's some control logic behind it. And then SAR, the SAR logic, just D flip-flops in a certain, being wired up in a certain way. And then you need the R2R DAC or C2C DAC, just a DAC DAC. If this is 4-bit, then the SAR is going to feed 4 digital lines to the DAC, B0, B1, B2, B3. And the DAC outputs the analog signal and feed it back into the comparator. Definitely the DAC need a VREF. Question for you guys. Is this signal analog or digital? This signal here. And why? And why is analog? Pretty legit answer. Yeah, that's right. You haven't converted yet. You just hold it there. It's a discrete analog voltage. It's not a digital signal. Digital signal is just 1 zeros, right? And this voltage can be anything. It's just a static voltage being held. It's not a square wave. It's a line. It's a line, can be anywhere from 0 to 5. Digital signals are 1 zeros, right? Or 0.05 volts. This is not. This is a stair. It's a line voltage staying there. It's just not varying as a sine wave. for example, so the voltage being held there can be one of these lines, okay? So this is 0 to 5 volts, and for example, this is 2.3 volts. Can I say 2.3 volts is a digital signal? It's not. So analog voltage, right, just being held there. It's not a square wave at all. It's just a line voltage. Okay, so the voltage here is these voltages.
So what's that image that you drew above?
This one?
Yeah.
That's a digital voltage. That's a digital signal.
Is that not the readout from the?
No, that's the readout from the ADC. If you can read out from the sample hole, you don't need the ADC anymore, right? And you're thinking are these one pin or multiple pins? Multiple pins. It's a digital signal, can only be 1 zeros. Where are these multiple pins? In here. Where? Where is the output? ICR is the output. Basically these ones, right? That's the output. That's the ADC's output. It takes multiple cycles to reach here because it has to. That's why we have to hold it there, right? We have to hold it during this period. We have to hold it there. So it takes time. So at the very beginning, it's not giving you the final result. At the very beginning, it's just the first value is trying to approximate the actual value. That's why it's called successive. It's trying 4 times for the 3-bit ADC. It tries 4 times to approximate that or to approach that real value. So at the very beginning, the first cycle, you are getting some values or digital output, which is not that accurate, but eventually it reaches the value the best this ADC can do. Depends on the resolution. So feed it back, so it get the first value and convert it back into analog voltage and come back here to compare to the real value here, to the value being held here, and then output a 1 0 to the control logic to determine if you want to adjust the values here. If it's not that close, you're getting a 1 or 0 depending on 1 or zeros. You plug in the 1 zeros or flip some of the digits to make it closer to the held value. And how it works, I'm going to show you maybe on Friday. So we have to do the quiz. The SAR algorithm is going to control which bit should be flipped or not. Yes, because you need to hold it there. If you don't hold it there, then during all the cycles, you're having different values, right? You need a one value. Yes. For one of the architecture, it's called delta and sigma. I'm not sure actually, sort of forgot. But it makes sense that during the conversion cycles, you do need a constant voltage to be there because it takes time to do all the conversions. Okay, you don't want that value to be changed, right, during the conversion. Okay, so the main point, the main part of the circuit, because this one is pretty simple, it's just holding the voltage there, so you don't have to change a lot of things over there. The comparator is just an op-amp. When you design ADC in the company, you buy the IPs actually, buy the IPs here, buy the IPs for $1,000 or something, you can buy it. And control logic usually is what the digital engineers will work on. They can either synthesize it or just draw by hand manually. The SAR is whatever is doable. You don't have to buy because it's very simple. I think the engineers are able to do it in the company. And the DAC, I don't think they have to buy it. But however, if you really don't want to spend time on it, you can buy the IP of the ADC. Don't want to spend time on designing anything, just buy it. $10,000. Okay, that's the quiz.